As we continue on here in lesson 11.5, we want to find the zeros of the function g of t given by factoring. So of course the first thing we look for is the greatest common factor, and we notice that both of the terms are divisible by 10 and they're also divisible by t squared. So if I divide out the 10t squared, 10t to the fourth divided by 10t squared is t squared, and 250t squared divided by 10t squared is 25. Well, you should notice then that the t squared minus 25 is a difference of squares, so it can be factored into two binomials. We square root the first term, we square root the last term, and then in order for the outside and inside products to cancel so that there's no middle term, as there isn't, we need one binomial with a plus and one binomial with a minus. So now the zeros. Well, we notice we've got three terms multiplied together. If any of those terms came out equal to 0, we would get a product of 0. So if we take the 10t squared and set it equal to 0 and solve for t, we'd find t is equal to 0. If we take the t plus 5 and set it equal to 0 and solve for t, we'd find t is equal to negative 5. And finally, if we take the t minus 5 and set it equal to 0 and solve for t, we'd find that t is equal to 5. If t were replaced with any of those three values, that polynomial would come out equal to 0. Now another target in this lesson is to be able to factor and find the zeros, is to be able to find the zeros by graphing. And so I give you the polynomial f of x written in red, and this time we want to, instead of factor, we want to do this by graphing. Well, actually we're going to do it by graphing and then we're going to factor, so I guess I do eventually want to factor. So we're going to enter this equation in y1, 2x cubed minus 6x squared minus 8x. And those are small coefficients, so this would fit in a standard viewing window. Although I know that I'm going to need to expand my y window a little bit. So I'd suggest you manually set your window such that x goes from a minimum of negative 5 to a maximum of positive 5. And you can count by ones in between there. And that y goes from a minimum of negative 30 to a maximum of 30. And you can count by anything you want. I chose here to count by 5. And what you'll notice when you look at this graph is that there are three x-intercepts visible. There's one here, there's one here, and there's one here. Now I would estimate that those are at negative 1, at 0, and at 4. But to be sure, I can go to my table in my calculator, second graph, and see if at negative 1, at x is equal to negative 1, if y is 0. And the same thing with the 0. See if y is 0 there as well. And then if y is 0 when x is 4. So our three x-intercepts are in fact negative 1, 0, and 4. So what we can do is we can write our three factors using those zeros. We're going to have three things multiplied together. And if any of those three things come out equal to 0, then we'd get a polynomial whose value would equal 0. So each one of those three things is going to need an x. Well, I wouldn't want to subtract 1 from x for this 0, because if I replaced x with negative 1, negative 1 minus 1 is negative 2. That doesn't come out equal to 0. What I would rather need to do is add 1 to x, because if I replaced x with negative 1, negative 1 plus 1 does come out equal to 0. For my second 0, I could either add or subtract 0. It wouldn't matter. And of course I can just write that as x as well. And once again, with the 0 of 4, I can't just add 4 to this x, because if I replaced with the x with 4, I'd get 4 plus 4, which is 8. And that's not equal to 0. I want it to come out equal to 0, so what I have to do instead is subtract 4. So basically what you do is you take each of your zeros and you put an x with them in your factors, but use the opposite sign. So we have 3 factors. They are x plus 1, x, and x minus 4. So using similar methods, we in this case want to write a polynomial function, just a general form of a polynomial function that has zeros at -2, at 0, at 2, and at pi. So in a general form, what we're basically identifying is, first, what are those zeros, or what are the factors, excuse me, for each of those zeros? Well, for -2, again, we said we'll need to put an x with it and use the opposite sign. So x plus 2 would be one of our factors, because if x were replaced with -2, that factor would come out equal to 0. For 0, we can just stick an x out in front, or x minus 0, whichever you prefer. For 2, we'd have a factor at x minus 2, because once again, if x were replaced with 2, that factor would equal 0. And for pi, we'd have a factor at x minus pi, because if x were replaced with pi, that factor would equal 0, and our polynomial would equal 0. Now this x out in front could have any possible coefficient. It does not matter what number I stick out in front of the x. Say 2x, well, if x were 0, that whole polynomial would come out equal to 0. So to identify that the coefficient of x can be any number, we'll just use k to represent any constant value. And we do this whenever we're asked to give a general form of a polynomial function. So p of x would equal kx times the quantity x plus 2 times the quantity x minus 2 times the quantity x minus pi. So once again, our targets for this lesson have been to find zeros of polynomial functions by factoring. Our first few examples addressed that target. Then to determine an equation for a polynomial function from data points or from the graph. We did that next. Third, to apply the zero product theorem and the factor theorem. So that's where we looked at each of the factors, set them equal to 0 to find the zeros. And then we graphed those polynomials, which was a continuation of our lesson 11.4. And finally, we learned to estimate zeros of functions of polynomials using tables or graphs, which again was a continuation of lesson 11.4. If you have any questions, don't hesitate to email me.